Welcome to the fifth and final video of the time complexity series. In this video, we're going to go over logarithmic time with a code example. Let's get started. So remember that logarithmic time just means that the runtime of our algorithm grows proportionally to the logarithm of the input size. And remember that the big O notation of logarithmic time is big O log of n. And if you remember from math class, a log without a base given is usually base 10. But in programming, we have base 2. I don't know exactly why they don't write log base 2 of n. I'm just guessing that it looks kind of bad if you write it like this. So there you go, big O log of n. And with a graph, you can see here, let's just, I'll keep that in there for now. So this is our big O log of n graph. And here I just specified big O, or not big O, log base 2. So here we have our log graph. As you can see, compared to our big O of n graph, that our growth is really small compared to big O of n, which makes logarithmic time much faster than linear time, as you can see through the differences in this graph. And what logarithmic basically means that in programming context, if we double our input size, our number of computations that we need to do only increases by 1. Whereas in linear time, it increases proportionally to our input size. So you can see here that, let's take some examples. Let's see at input size 2, we only need 1 operation, but in linear time, we need 2. And now if we double this to 4, we get 2 operations, and we get 4 over here. And then if we keep doubling it, you'll see that the logarithmic time only increases 1 number of computation every double versus the linear time just doubling. So I'm just trying to emphasize that logarithmic time is much more efficient than a linear time. Let's move on to a code example. So a code example for logarithmic time, the most popular one is usually binary search. And binary search is just an algorithm where we split the time every iteration to search an array. So we're going to split the search array into halves every iteration. And let's just create a sample array. And for this binary search to work, we need a sorted array. I'm just going to make a sorted array in ascending order like this. If you don't have it in ascending order, you can just use the built-in Python search function, but usually you won't have to do that. So let's just keep it like a sorted array for now. And the goal of a binary search is to find the index of our target number. So right now I'll just keep our target at 10, and let's create our binary search function with our inputs arguments being the nums array and the target number that we're trying to find. So the approach for this is going to be that we have 2 pointers. We're going to have the left pointer being 0 and the right pointer being the length of our array. And what we're going to be doing is we're going to be taking the middle, or we're going to be finding the middle of the intervals that we create. So the first interval will be obviously from the 0th index to the last index of the array. So the middle index of this would just be 3. So our search would start off at 6. So let's create a loop that ends when the left array, or the left pointer, is less than or equal to the right pointer. And then let's create our middle index. So our middle index, there's 2 ways that we can do this. The most straightforward way that we can do this is we add the right pointer to the left pointer, and then we divide it by 2. And this is a way that you can do it, but as our input size grows, this might not be the best way to do it because we can run into integer overflow errors with this method. A more or a most less concerning method is we can subtract the left pointer from the right pointer, and then we're going to add the left pointer again. So we're basically finding the middle index, and then we're adding the left counter again to find the middle index of the interval that we're looking for. Or this is like our half index, and to find the middle index we're gonna add the left back again. So now we're gonna need some conditionals here. So the first conditional that we're gonna do is we're gonna check if the middle number is equal to the target, and then obviously if we find that it's equal to the target, we're just gonna return the index. And remember that our mid variable is gonna be the index that we're searching, so we can just return that. The next thing, or the next conditional, it doesn't really matter which order you do it in, but we're gonna do if the nums mid is greater than the target. So say our target is 10 and our first search is going to be 6. Actually, for the example, let's say if the nums, or if the number is less than the target. So we have our target equals to 10, and our first iteration we're going to have 6 as our nums mid, or our middle number. So obviously 6 is less than 10. So since this is a sorted array, we know that every number below the middle number is going to be less than the middle number. Therefore, it can't be equal to the target number. So we can just eliminate this half of the array. And how we're going to do this is we're going to set the left counter equal to the middle index and then add 1 to it. So we're going to start, our left pointer would now be index 0, 1, 2, 3. So now we can do the other, or the opposite of this. So if the middle number is greater than the target, so let's see in our array here, let's pick another number. So just say that our target was 4, and obviously our middle number is still going to be 6. Since 6 is greater than 4, we know that every number after 6 cannot be equal to 4, because every number after 6 is going to be greater than 6 in our sorted array. So we can eliminate these numbers, or that half of the array. And how we're going to do this is just create or set the right counter or pointer equal to the middle index minus 1. And yeah, this is the basic structure of binary search. And if we don't find the number in the array, we're just going to return -1, which is usually what binary search questions ask you to do. So yeah, this binary search should work. Let's check if it all works, if it all right. Yeah, everything looks right. Now we can just test this binary search, and then we'll put array and target. And let's see, this should print out 0, 1, 2, 3. This should print out 3. Let's try this. And there we go. We got index 3. And this is big O of log n, because, or log base 2 of n. That's our time complexity, because we're cutting the search time of the array in half through every iteration that we go through. So yeah, that's logarithmic time.